Okay, so now we'll look at the social network with weight, height, and age of users given to you. And using all these three features, we want to assess the network level similarity among the nodes. So our k here is 3. Okay, so you could feed in this raw data to the pairwise similarity program, and of course you just have to include the numbers. You should not include any text like word text, byte, pound, height. That's the text. You should not include that. Just include the numbers 1, 130, 55, 23, and so on in the text file. And um, enter the pairwise distance matrix. Okay, and this is going to be the pairwise distance matrix. So now what we are going to do is k is 3, so square root of 3 is going to be 1.7320. So that's going to be the value of right index. Remember in the previous example we used square root of 2 because it's a two-dimensional coordinate system. So here we have to use square root of 3 as the maximum possible distance between any two nodes because it's a three-dimensional coordinate system. So left index is 0, right index is square root of 3, which is 1.7320. So now, of course, as you can see, the pairwise distance between any two nodes in the matrix is going to be less than 1.732. So you're going to have a edge between any two vertices. So it's a complete graph. So the graph is going to be connected at the right index, and of course, um, other than the diagonal, which is the vertex to itself, all the entries are greater than 0. So if the threshold distance is 0, then we're not going to have an edge between any two vertices. So the graph is going to be disconnected at left index value of 0. So those are initial left and right index. Always we maintain an invariant that the graph is not connected at left index and always connected at the right index. So the middle index, which is the average of 0 and 1.7320. So the middle index is always the average of left and right index, is 0.8660 in this example. So if you use this as a threshold distance and you go back to the pairwise distance matrix, you can also notice every entry in this pairwise distance matrix is less than 0.8660. So we are going to get a complete graph like this, and this middle index is as a threshold distance. So that means we can move the right index to the left and set the right index to be the middle index, because again our goal is to find the minimum threshold distance given this distance matrix. We want to find the minimum threshold distance that will give us a connected graph of these 7 vertices. So since the graph is connected at this threshold distance, when the middle index is used as a threshold distance, it's going to stay. It is going to be connected even if you go above than this value of the threshold distance. So we'll make the right index to move to the left by setting the right index to be this middle index value of 0.8660. So the new left and right index are this, and so the middle index is the average of these two, which is 0.4330. So if you go back again to the distance matrix, all the entries are going to be less than 0.4330. So again we get a complete graph. So move the right index further to the left by setting it to be 0.4330. So the new middle index is average of the left and right index values, so it's 0.2165, and you see some node pairs are going to have a distance greater than the 0.2165. So for example 1, 2 have a distance of 0.241 that is greater than 0.2165. So you don't have an edge between 1, 2. So use the previous iteration graph as a basis and remove those edges whose node pairs have a Euclidean distance that is greater than the threshold distance value. So now what we'll do is, let's check if the graph is connected. The graph is still connected. So use the right index. Set the right index to be 0.2165, and the new middle index is 0.1083. So now use this as a threshold distance and check if the graph, check check what node pairs have a distance that is greater than 0.1083 and remove the edges from this graph. And what we get is a graph like this, which is obviously not a connected graph. So set the left index to be 0.1083 because we see that the graph is not connected at the threshold distance of 0.1083, so it's not going to be connected if you go less than this either. So we can move the left index to the right and set the left index to be 0.1083. So now using these two values, find the middle index, which is 0.1624, and check the node pass. So now this iteration graph was not connected, so we have to use this graph as a basis, and since the threshold distance 0.1624 is less than 0.2165, it's reasonable to use this graph as a basis and remove those edges whose node pairs have a distance that is greater than 0.1624. So you see, for example, 5,7 had a distance of 0.1851, so that means it's greater than 0.1624, and 0.1851 is obviously less than 0.165. That is why they have an edge here on this graph, but it is greater than 0.1624, so we remove the edge between 5 and 7. Now you see that this graph is still connected, so that means the right index can be set to 0.1624, and we can compute the middle index to be average of the left and right index values, which is 0.1354. So that means on this graph, which is a connected graph, we check if any edge has distance greater than 0.1354 and remove that edge. And that would be, so for example, 26 has a distance 0.1506, which is greater than 0.1354. So we remove 26 from this graph. So likewise check for all the node pairs that have an edge here and the distance. If the distance comes out to be greater than 0.1354, we remove them in this graph now. Now, is this a connected graph? You have to be careful. This was a connected graph. If you look at it closely, yes, because we can go from 1, 3, 6, and then from 6 we can go to 2, 7, 4, 5. So through 6 we can make 1 and 3 also to be reachable to 2, 4, 7, 5. On the other hand, this graph you have it from 3, 1, 6, and 3 and 6 are not connected, of course, but we can go from 6 to 1 and then 3, so that they are reachable. But 3, 1, 6 in no way has an edge with 2, 4, 5, and 7. So that means it's going to be two components. One is 3, 1, 6, the other is 2, 4, 7, 5. So it's not a connected graph. So that means the left index can be set to be 0.1354 and the right index is 0.1624. The new middle index is 0.1489, and we check if we use this as a threshold distance, can we get a connected graph. So since this graph is not connected, we will have to use this as a basis and check if the edges in this graph have a distance greater than or less than this 0.1489. If the distance of the edges in this graph is greater than 0.1489, we remove that edge. Say for example, this edge between 3 and 6 has a distance of 0.1512, which is greater than 0.1489, so that there's no edge between 3 and 6. And you can see this is same as this graph here, so it's basically not a connected graph. So you can make the left index to be 0.1489, right index is 0.1624, the middle index is 0.1557, and that will lead us again from this graph, remove those edges that have a distance greater than 0.1557, so we get basically almost, this is the same graph, and this is a connected graph. So we can make the right index to be 0.1557, the new middle index is 0.1523, using this as a threshold distance on this graph and check if any edge on this graph is having a distance greater than 0.1523. The answer is probably not, so we get the same graph, it is a connected graph, so we can make the right index to be 0.1523. Now as you go through each iteration, check if the absolute difference between the left and right index has become less than the termination threshold. Okay. Now the middle index is average of left and right index, which is 0.1506. Now is this graph connected? Um, there's an edge between 2 and 6 now, but no edge between 3 and 6, right? So we can go from 3 to 1, 6, and then through 6 you can go to 2, 4, 7, 5. Yes, so this graph is connected. So we can make the right index be 0.1506, left index is 0.1489, the new middle index is 0.1498. So remove from this graph those edges that have distance greater than 0.1498. So our edge between 2 and 6 has a distance of 0.1506, and that's greater than 0.1498. So this edge 2, 6 goes away. So we now, it's not a connected graph. So we can make the left index as 0.1498, right index stays at 0.1506. Now you see the difference between the right and left index has become less than 0.001. So we stop the iterations, and the latest value of right index 0.1506 is now used to compute the network level similarity index. So 0.1506, which is the latest value of right index, divided by square root of 3. Again we divide by 3 because we're looking at 3 dimensions, 3 features. So 1 minus of that 0.9130 is the network level similarity index. Now as a practice, as I explained earlier, you can change, or I explained in the previous topic, instead of 23 and 50 for the age for vertices 1 and 5, you can make it 3 and 5. Okay, and you can practice and this algorithm and compute what is the network level similarity index. It will be less than 0.9130 because you are decreasing the similarity among the vertices. Okay, so we'll stop the video with this.